Hello, 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 hello. Welcome all of you for today's live session, the second live session for Economic Operations and Control of Power System NPTEL course. So today is it's a very important session, and we will be going through the brief overview. It will not be a brief; it will be a good exclusive overview of this week too, because it covers very important subject matters, some preliminaries, and also a very important but simple but a very important power system operation tool, which is economic dispatch, and which is now used in several sophisticated uh, ways. We'll be only studying a simple form of that tool, but in reality, in practice, sophisticated versions of that tool are considered. Let us begin. This will be the agenda which we have been following since the last live session as well. We will go through the overview of week 2 material, then discuss some questions. Just to remind you, these are the deadlines for assignment 1 and 2. The deadline for both the assignments is tomorrow, which is August 7. So please submit the assignment by tomorrow. Then we have, I hope all of you were able to access the live sessions recordings and also the material which was uploaded regarding that week. So we'll begin with the week 2 overview. In week 2, we discussed these three things. Let me use the marker. So we discussed these three things. One is dynamic programming, economic dispatch of thermal units, and then economic dispatch using numerical methods. So both are economic dispatch only. Or short form is ED, which I will also be using many times. You can remember this. It's economic dispatch. This will include different methods for ED. Here we will develop the basic concept of ED. And some of you might be already familiar with that in BTech. In your undergrad course, you would have studied the most simple formulation of ED. We will just extend it to a next level. And we'll see different methods for that. Starting with the dynamic programming. First topic was the dynamic programming, which was covered in the week 1 session. It was developed in 1950s, around 1950s by Richard Bellman. The use of dynamic programming is to solve combinatorial optimization problems. Here, unit commitment in power system is one of the combinatorial optimization problems because it involves binary decision variables regarding the on or off of a thermal generator. The generator can be on or off, and as a result, unit commitment becomes a binary or integer programming. And for such optimization problems where integers or binary variables are included, dynamic programming can be used. And also, one important thing is dynamic programming can be used when we have small sub problems which can be combined to make the overall problem. In those cases only we can use dynamic programming. Unit commitment, we can, yeah, we have small sub problems for each time block and we can combine them together. The result, the advantage of dynamic programming is that it gives us exact solution and it also guarantees optimal solution. Power system, pertaining to power system, we have two applications, ED and unit commitment also. Other applications are like capacity expansion planning. So one may think, what are the binary variables here? So binary variables include whether a transmission line should be erected or not, whether a new generator should come up or not. And now we can say even renewables and storage, whether a new energy storage should be installed or not. So these types of binary variables are available in capacity expansion planning. We have three important terms in dynamic programming. One is stage, then state and policy. For each stage, we have different states, and one of them is part of the optimal path. Policy is the different path available at each stage, different alternative actions we'll see. And then the principle of dynamic programming is that an optimal path which we have selected should always contain optimal subpath or policies. And there are two methods, forward and backward recursion methods. In forward, we find the optimal path for the first node and we move forward. That's why called forward recursion. And opposite, in case of backward, we find the optimal path for last node and move backward. This is a simple example. One example, if we compare the two types of algorithm. One is a greedy algorithm, which at each step tries to maximize. Looks for the immediate benefit. However, on the other hand, the dynamic programming will look for the overall benefit. If we see here, if we move from here to here, so this is stage one. This is stage two. This is stage three. We are moving from here to here. So from here to here, I hope, Shiva, I'm audible. Can you hear me, Shiva? Shiva, am I audible? You can type in the chat box also. Just wanted to confirm that I'm audible or not. Can you please confirm, Shiva? Hope I'm audible. Okay, thank you for confirming. So, we just started with a brief overview of week 2. It will not be brief because several mathematical concepts were available. We'll discuss, so we will discuss all the concepts. These are very important. We're starting with the dynamic programming. It's a simple example. Greedy algorithm looks for the immediate benefit. If we move from A to E, then or from this level to this level. So on stage 1, we see this path is the most economical. If we reach here from again the transition, if we traverse, then after after reaching E point, the most economical, we have only two options, 4 and 11. The 4 one is the cheapest. If we reach F, then there is only one way. The total cost is 1 plus 4 plus 18, which comes out to be 23. But if we employ dynamic programming, then we get this path 5 plus 2 plus 2. Which one? Dynamic programming is better. So this results in suboptimal solutions. Dynamic programming gives us the optimal solution. It guarantees optimal solution. That is why it's a very good method. So this is one example, simple example. We'll just go through it. I will just solve it. If do you want me to solve it, or we can move ahead? I will just answer. I will give the answer for this first. This is the overall cost. The minimal cost is 20, and this is the route which will be followed. We can do it both ways, by forward or backward recursion. In forward, the optimal path will be found for start the first node, A node, and we move in the forward direction from A to J. While in the backward, we find the optimal path for the last node and we move backward, we track backward. Let us move forward. If time is available, I will solve it also. Then the next topic which was discussed was economic dispatch. Now this is going to take time. We will discuss everything so that you can solve the questions. If some numerical questions are also available, although in the assignment, very simple numerical problems are given. This is the basic idea of economic dispatch. We have generators. Let's say n generators are there, and we want to meet the load with the minimum cost. We want to determine what each of these generators should produce or generate to meet the demand, to satisfy the demand at the minimal cost. So this is the most basic method which was which was used when the power system began. And initially we had only simple 2-3 types of generators, and we have been working with them for last so many years. These are nuclear, which act as the base load plant. Because this is a base load plant, its generator, its output, it is almost constant. Some PG fixed, I will say. Because changing the generator, the nuclear output is not economical. Moving it again means reducing it and again increasing it. Varying the output of nuclear is not economical. So that is why it is almost constant. If we have such kind of a demand curve, let's say, then we can say that this, because nuclear it generates almost a constant level value of so its output is almost constant. So this part of the curve, we can say this area, this rectangle is this total area means energy over, let's say it's for 1 day. So this energy output for the day will be provided by the nuclear plant. This is the base of this curve. If we say the entire area, then this is the base of that area. And that area is served by nuclear, so they are also called the base load plant. And above them, this part will be served by other generators like thermal, hydro, gas, other. In hydro also, so here generation is fixed. Okay, if generation is fixed, in optimization, if we include constant term, then cost is anyhow already fixed. Operational cost is not, generation is fixed, so cost will also be, operational cost is also fixed. So in optimization problem, if we include constant term, then it will have no effect. Then second term, hydro, they have a constant operating cost till their rated capacity. So that is also a constant in the optimization problem if we have. So third one, we are left with the thermal. That's why this economic dispatch problem we solve for the thermal plants. They have their operating cost characteristics, which is the fuel cost characteristics. Other costs like labor cost, maintenance, they are fixed. So mostly it is dominated by, is primarily driven by the fuel cost characteristics, which is this. This is the fuel cost characteristics. Is AP square BP plus C. It's a quadratic cost curve which has a minimum and maximum. These are the technical limits, minimum and maximum. We need to respect them. The problem formulation for economic dispatch is like this. We want to minimize the overall cost, total cost of generation, where for all the generators, so let's say we have n generators. So we need to sum the cost of all the generators, all the n generators 1 to n. Subject to, we have these two constraints. First is the equality constraint, which is the power balance constraint, that total generation. This is total generation should be equal to total load, PL. And each of the generators should be within its Pmin and Pmax. We saw because of its characteristic curve. There is a minimum and maximum limit for its generation. And then we solve it using the Legrange multiplier. So this, our cost function was this. Fi Pi summation. The Lagrange multiplier is the it is summation of the objective function plus lambda times the constraint. So here this is the constraint. PL minus Pi. And then we differentiate it with respect to all the, so here it's a function of P and lambda. All the Pi and lambdas. We differentiate it with respect to both. If we differentiate with respect to lambda, then this is 0. And we get the same equality constraint. But with respect to Pi, we will get it as dFi by dPi. And this PL is a constant. Here it is summation of PIs. So with respect to each PI, there will be one negative sign. So this will be dF by dP minus lambda, and this has to be 0. So for each generator, the incremental cost is equals to d lambda for each generator. I is equals to 1 to n. If we have 3 generators, then dF by dP1 is equals to dF by F2 by dP2 is equals to dF3 by dP3. And this is equals to lambda. And if we have quadratic cost curve, then this is 2AP A1 P1 plus B1 is equals to 2A2 P2 plus B2 is equals to 2A3 P3 plus B3, and this is lambda. And so here we have 4 variables, P1, P2, P3, and lambda. But these are only 3 equations. So we have one more equation, which is this. PL is equals to P1 plus P2 plus P3. Now we have 4 equation and 4 variables we can solve. So using this equation, we can directly write lambda as P load plus summation of BI by 2 PI divided by summation of 1 by 2 AI. And if we have lambda, we can find out PI like this. So once we find out PI, then we have to verify these conditions. If we find that PI is between its minimum and maximum limit, then if all the generators are within this limit, within their limit, then their incremental cost will be same, and that will be equal to lambda. But if a generator hits its minimum limit, sorry, maybe maximum limit, let's say if a generator hits its maximum limit of PI max, or let's say if we find out P1 and we find out that P1 is even greater than P1 max, but we have to respect the limit, so we limit it to P1 max only. If generation is going beyond its limit, that means that generator is a very cheaper generator. That's why this problem is trying to generate more power from that generator. That means its incremental cost is less as compared to the other generators. That is why if a generator hits its maximum limit, its incremental cost will be less. We can see here. So df by dp is less than lambda if it hits the maximum limit. If it hits the minimum limit, because of the constraint, we have to ensure that a generator cannot generate below P min. That means it's a costly generator. Its incremental cost is very high. We want to get only minimum from it. First, we will try to take power from the other cheaper generators. Now, this is without network losses. Now, if both the generators, let's say there are 2 generators and both the generators are connected on the same bus or they are very close, and if we say that incremental cost of generator 1 is greater than generator 2, then generator 2 will be preferred because it is cheaper. But if they are separated by a transmission line, they are little bit far away, and still the same condition holds that incremental cost of 2, although 2 is cheaper, but still it may not be economical to send power or to supply this load because it may be uneconomical due to losses involved. If we ignore the network, then the output will be different. With losses, we need to consider things will change a bit. Now earlier the problem was like this. We had generator and no network directly feeding the load. Now network is there. We have included the network here. So we have to consider the formulation will change now. Earlier this was was equal to summation of generator, but now load plus losses need to be supplied by all the generators. Their sum has to be equal to load plus losses. And this is same. Again, we can write the Legrange multiplier for this and we find that equation is like this. Dou fi by dou pi plus lambda into this is incremental loss for the ith generator, which is equals to lambda. So lambda comes out to be like this, where this is penalty factor and it is equals to 1 upon 1 minus the incremental loss. If we have the loss, some formula for loss, we can easily calculate this. And we can, from here, we can go to that previous case also. If both all the generators are connected to the same bus, then this becomes equal to 1. Because there is no loss in that case. This becomes 0, no change in loss, and this becomes 1 again. So same thing. Without network, we reach the same result. These two equations are called coordination equation because we see this loss function is a function of power. This is a function of power and this is also a function of power. So it becomes all non-linear. And also we don't know. So loss is also a function of power. And we don't know loss beforehand. So that is a problem. Transmission line losses depends on the current and current depends on the power. And power we don't know. So we know loss only once we calculate current, which we only know when we know the generator's output. So loss cannot be calculated beforehand. So that's why we need to assume some initial guess and we have to iterate. So it needs to be an iterative procedure. There are two ways. Either we have a loss formula. These are empirical formulas. We can use them and both of them will require a iterative solution, or we include power flow equations which have the losses modeled within them. So that this is also nonlinear. Both are. This will also require iterative procedure. We use these Newton-Raphson methods and other methods. I mean, all the nonlinear solvers they will follow a iterative. Even linear solvers they all are all of these optimization solvers are iterative solvers. The overall conclusion is that we need iterative solution for that. We cannot get it directly. These are the steps for that iterative method. We can start with the initial generation, which is the sum of generators, such that the values can be taken such that sum is equal to loss. Sorry, load. Sum of generator is equal to load. And then because we know now P1, P2, P3, which we have assumed, some this is we can call it as initial guess. It is an initial guess. Then because we know we have this initial guess and also we have the loss formula, and this using the relation that we have seen here, we can calculate, we can solve this equation because we know pi we already know. So using this equation, load is known. So we can find out loss using the loss formula, and then we can also find out this. Because we know the loss formula, we can differentiate and find out P1. These all the incremental losses as well as the total loss. Then for each iteration, they will be considered as constant. Then we can calculate lambda such that now because we know loss using the loss formula, we know this also and we know this from the loss formula. Because we know loss, then we can find out lambda using this, which satisfy this equation using the coordination equations. And again, we will find out P1, P2, P3. Solve for P1, P2, P3 here. Find out the lambda first and then using lambda find out P1, P2, P3 again. These P1, P2, P3 will be different from what we have assumed. Then we find out the difference. This is called a norm. infinity norm. We say, suppose there are 3 generators. So this means maximum of P1 minus P2 mod absolute value. P1 K, P1 K minus 1. Previous iteration. So if we call, if we get P1 dash, P2 dash, P3 dash from here, then this will be maximum of P1 dash minus P1 absolute value, P2 dash minus P2, and P3 dash minus P3. So whichever is, we track the maximum, and if that maximum value is less than the tolerance which we have defined, maybe 10 is for minus 3, 10 is for minus 4, something, depending upon how accurate we want, up to what decimal places. If this is satisfied, then we stop. Otherwise, we again go to the step 2. Again, we calculate this new loss using the loss formula because we have new values of P1, P2, P3, and same procedure. So it's a very simple thing. We just have to use these equations which we have already defined and then keep on repeatedly calculating until we converge. Any doubt in this procedure? If you have any doubt, you can ask in between also. There is no problem. An important thing of this today's session is these different methods used for solving economic dispatch. And these are the preliminaries. This was discussed in week 3. This was not week 3, lecture 4, lecture 3 of that week. And this is for the last lecture of the week 2. So initially when these methods were developed 30, 40 years back, computers were not good for large calculations. Now we have very fast computers, processors. We can solve very complicated problems also. And that's why at that time, because computation was a problem, it was a bottleneck. Everything was ensured. We used to ensure that everything is converted into a linear programming framework. That means the constraints are linear and the objective function and constraints, everything is linear. We want them linear. We have already seen that our cost curve for a generator is AP square plus BP plus C, which is non-linear. This is non-linear, it's a quadratic curve. It's a non-linear curve. But we want everything in linear framework. Therefore, we want to linearize this quadratic curve. This is a quadratic curve and we want to linearize it. We can take different steps and increase the steps, and let's say I take only 2 steps and let me change the color. If we take only 2 steps, these 2 steps, say this. Let me draw it again. It's not so clear. Since I have a figure, we can better. I will show you the figure only directly. We'll just that's why. So quadratic curve, we want to make it linear, but it is not fully linear. It is piecewise linear. We have different steps of linear curves, linear functions. Quadratic to linear we want. And then next thing was discussed, which is participation factor. That also we will see. Then composite generation production cost. If we have a set of generator, can we each generator has its own curve, characteristic curve, cost curve. But if I have n generators and each of them have their own characteristic curve, but I want only one characteristic cost curve for this composite generator, combined generator. That how can we do that? So that is this composite generation production cost method for doing that. Then using this, here we have not this one, but here we have piecewise linear cost characteristics, and we want, so earlier we were using the objective function as this, and this was quadratic. Now we want to make it linear. So how to do that and what things will change, that we will see in this. Linear programming economic dispatch with piecewise linear cost function. Without network and with network. And last thing, in last lecture, what was discussed is there's different numerical methods for calculating, for obtaining economic dispatch. First one was iterative method, where we increment lambda depending upon the where we fall, depending upon the error from the previous value. The next one is the gradient method, moving in towards the direction of the steepest descent. The minimum, it's a function like this, and we this is the optimum value x star, and if we start from here, then we want to move in this direction, or if we are here, we want to move in this direction, because it is descending, the function cost is reducing here. If this is function value, in our case it is cost, so it will reduce. So that's why we are descending onto the curve. So it is in the direction of steepest descent. If it is maximization problem, then it will be steepest ascent. But convention is to consider minimization. If we have a maximization problem, then we can make it minimization of minus fx. That's why we generally use minimization, and for us it's cost minimization, so it's minimization only problem. Then there are some problem with gradient. We move to improved gradient. We'll see all this. Last one is Newton's method. So this is the first one, piecewise linear cost function, which I was trying to draw, but somehow it was not good. But here you can see it very clearly. We have three steps here. So initially we have the quadratic cost curve. This is the first one. You can see here. Same quadratic cost curve, but here it is shown by using only 2 breakpoints and here 4 breakpoints. So here 2 breakpoints are the same, the minimum and maximum limit of the generator itself. If in between these 2 points, if we just draw a line, if we connect these two by a straight line, then we get a single segment linear cost characteristic. So this is linear. There are no pieces, it's a single piece. It's a linear cost curve, incremental cost curve. So it's a linear cost curve and its incremental cost curve will be its differentiation. And because it's linear, its differentiation is constant. So this becomes the marginal or incremental cost curve. It's a constant. This is for only one block or the two breakpoints, which are its technical limits. Here we have three blocks or three segments by having four breakpoints. Two are the minimum and upper bound because of technical limits, and then we have two additional P2 and P3 in between. And because of 4 points, we have three segments, S1, S2, and S3. We have three segments. This is now because it's a combination of three linear curves. It is called a piecewise linear. It's a piecewise linear. So in pieces, we are linearizing this cost curve. So we are taking four breakpoints. Between these two breakpoints, we are making one linear approximation. Then between these 2 points, we are making another. And so we have 4 points and three segments of linear curves. If we differentiate this, we get this incremental cost curve. In this case, we have a stepped curve with constant values in between the breakpoints. These are three different constant values. This is the step. These are the steps. First, we have the quadratic cost curve. We depending upon the breakpoints or how many segments we want, we can generate breakpoints, and then we can divide these segments. We can calculate the slopes because we know the function, we know these values. We have this quadratic curve. We have equation of this curve, and we are joining these 2 points. That means the value, the function value is same here, whether it's linear or quadratic. AP square plus BP plus C, we can use it for these at these 2 points and calculate the values. And then we can calculate the slope. How we can do that? How can we do that? We can calculate F at P2 minus F at P1 divided by P2 minus P1. So this will be the slope for the first segment. Similarly, we can do it for all the three segments. This way we will have S1 slope of each curve. And once we have slope, we just differentiation will be its slope. S1, S2, S3. We have this piecewise linear cost curve, then we differentiate it, we get the incremental cost curve or the marginal cost curve. Now, how can we use this incremental or this, let's say the piecewise linear cost curves? If we have, let's say what we were doing previously, we had three generators, like P1, P2, and P3, and we wanted to know how are they going to supply this load, how much they should generate. But there we considered quadratic cost curve. Now here we have linearized it, piecewise linear. Now we again want to ask the same question, how much each of these generators should produce to satisfy the demand. That we can do it very easily by using this method. You can see here what we can do. First of all, we have these three generators. These are I have already divided them into using 4 breakpoints. You can see the minimum of P1 is 100, maximum is 300. For P2, minimum is 50, maximum is 250. For P3, minimum is 40 and maximum is 350. And in between, 2 breakpoints have been considered. One is for P1, it's 180 and 240. For P2, 120 is 170, and for P3, 120, 250. So for each of them, we can calculate the slope. And the slope is same as the incremental cost for that block or segment. So I call it marginal cost or incremental cost. For each block we can calculate. So lambda 11 means this first subscript is for generator and second one is for the block. So for these three are for the first generator. So lambda 1, lambda 1, lambda 1, 1, 2, 3 are the blocks. So lambda 1, 1, 1, 2, 1, 3 for first generator. Similarly, 2, 1, 2, 2, 2, 3 for second, and 3, 1, 3, 2, 3, 3 for third. We calculate all these segments, the slope of these segments. Then we order them in the increasing order. because we already know that the generator with the minimum incremental cost will be scheduled first. We order them. Here we can see the first segment of third generator is having the least incremental cost, 13.24. We order them. This is the order, ascending order. Lambda 3 1, lambda 1 1. This is lambda 1 1. Then lambda 2 1. Similarly, you can arrange it. Right? So this is the first step. First step is this: make this quadratic cost curve into piecewise linear and calculate the slope for each of the segment. Then second step is to order them. Order them in the ascending order, because in that order we are going to use them to satisfy the demand. Okay. So here the demand is, this is how much? 260 and 500. So we want to satisfy a load of 500 megawatts. This is correct. This is 100 plus 290. Nine 48. You know, I have made some mistake. 20, 20. Five hundred. Okay. I think I have, yeah. Somewhere here I have made some mistake. This difference is, this is not correct. If it is 500 and this is how much? This is, I have summed this. This is should not be 190 here. This is not correct. It should be difference between this 500 and 190. So this will be how much? 190 plus this difference plus 80. So it is 270. And 310 plus 190 is okay. And this is 80. Now this is correct. So this should be 310. Sorry for that. The load is 500 and this should be 310. Yes, once we order it in increasing order, the first step is to load each of the generator with their minimum value, because we have the constraint. We want to supply the load. All the sum of the generation should be equal to load. Plus we have one more constraint, that each of the generator should be more than its minimum and less than its maximum value. So we know that each of the generator will at least has to generate minimum value. And the minimum value for generator 1 is 100, for 2 is 50, and for 3 it's 40. We load each of these generator with their minimum values 150 and 940. So sum is 190, and so difference here, load 500 minus this sum 190 is 310. Okay. Now we use these blocks. Now we use the this block, first block. Okay, first block is above, over and above this P minimum already. And the width of this block, first block is 80. 80, so we can directly use 80 because this is minimum. And if we add 80, this first block, which is cheapest, is for generator 3. The first block of generator 3, this. And its width is 80. So it can generate 80. We add 80 to this P3. We add 80 to this, then it becomes 120. Now the sum becomes 230, sum becomes 270, and difference becomes 230. Okay, sum is 170 plus 270 and difference is 230. Now this is correct. So this should be 310. Now second one is this first segment of or first block of generator 1. Same, it has also capacity of 80. We add 80 to this first generator. It becomes 180. Other remains same. So in each step we are using one block. If any of the generator reaches its maximum limit, then we have to stop there, or that block exhausts, then we go to the next block. Here this block is exhausted and P1 is not yet has not yet reached its maximum value. Its maximum is 300. We can continue with that. So this is 180 now, and the difference becomes 150 now. Because this is 170, this becomes 350 and difference is 150. Next block is this first segment of generator 2, and it has a limit of 70. We add 70 to this second generator, it becomes 120. 120, 380, 420, now difference is 80. Again we move to the next block, which is second block of the first generator, and it has a capacity of 60. We add 60 here. This becomes 240 and 480 and difference is 20. Next block is this. We want, it has a capacity of 50, but we only want to meet 20. We add this to the second block, second generator. We add 20 here. The final solution becomes P1 will generate 240, P2 140, and P3 will generate 120. So this becomes the final solution. Now, if instead of 500, the demand is more, let's say it is 6, let's say it is 700. Then what are we going to do? Then we utilize this fully. In that case, the difference, if in that case, the difference here will be plus 200. So it will be 220. If we use this one, 50 here, then 50 we add here, generator 2. This becomes 70. This becomes 170. So now difference becomes, this was 220, 50, so it becomes 170. Now we can take the other next one. This is third segment of first generator. This is, its capacity is 60. So we add 60 to the generator first. This becomes C1 300. So P1 has reached its maximum limit. P2 at 170, P3 at 120. Now this difference becomes 110. Next block is this. And its capacity is 130. And the demand, we only need 110. We can add 110 to the third generator. 110. So P1 becomes 120, 300, P2 becomes 170, this becomes 230. And 230 is below its maximum limit, which is 350. This becomes a solution for a demand of 700 megawatt. Okay. This is a very simple procedure for piecewise linear generators, cost curves. If we have quadratic curves, we cannot do it manually, right? We will have to, in this way, simply, in this such a simple way, we cannot do. We will have to use that formula, which we have derived for lambda and pi, and then check the conditions, those conditions. But for linearized cost curve, piecewise linear, this becomes a little more easier. So this is the way you can do it. Now moving on to the base point and the participation factor. This also we have discussed. This is the incremental cost curve, which is a linear cost curve. So if it is cost curve is quadratic and its incremental cost is linear. This is used when participation factors are used when we want to, because if system is very large, then solving a linear program may take time. But I want a quick solution. Let's say within 15 minutes, we have to dispatch the generator. We have to give them, we have to tell the generator, we have in 15 minutes, the generator remain constant. In India, we have 15-minute time lock. We have dispatch for every 15 minutes. So for next 15 minutes, it will remain same. The generator needs to be told, let's say this is T3, this is T4, T2, T1. And this interval is 15 minutes. So within 15 minutes, I have to do everything. We have to calculate dispatch and see the solver has to calculate, then it has to be verified whether it will, all the generation schedule is going, is not, whether it will violate any network limit or not. We don't want that. Everything has to be done within 15 minutes. For that, solver has to be very quick. And if we can have something where we need not calculate, do this economic dispatch again for small changes in load. If load changes there is a very small change in load, then can we use something where we can directly have some formula instead of again doing economic dispatch for a large system? Because in a large system, there are several thousands of generators. If we can have a simple formula for that, then it can help us when there are very minute changes in the load. So that is the objective for motive for developing these participation factors. And so this is obtained from the Taylor series expansion. And we get this for each generator we have change in incremental cost divided by the second derivative of the cost curve. Because it's a quadratic cost curve, second derivative exists. But if it's already linear, then second derivative does not exist. It will be, it's zero and we cannot do this. So this is can be done for quadratic and above quadratic cost curves, higher order cost curves. For each generator, we have this and summation of changes in generator. This is change in generator for a change in load. So, and the sum of changes in individual generator should be equal to the change in the load. The change in load has to be met by these two generators. If we have only two generators. And for each generator, we have delta lambda divided by F1 double dash plus delta lambda divided by F2 double dash, and this is equals to change in demand. And if we take this ratio delta Pi by delta Pd, then it becomes 1 by F I double dash. Or if it is P1, then it will become F1, and here it will be 1 by F1 double dash plus 1 by F2 double dash sum. In this way, we can calculate this ratio, and if you want to calculate the new generation, then it will be simply the old generation, which is the base generation, plus this delta Pi by delta Pd multiplied by delta Pd. And this we already know, it is 1 by Fi double dash summation of 1 by Fi double dash. This is easily known from the cost curve. Delta Pd we know this. We can calculate the new generator. New generation. Same thing is mentioned here also. Same. So this will tell what percentage of change in demand should be met by this generator. Now composite generation production cost. If we have n generator and we have another generator which has some constraints, fuel constraint, but other generators don't have such fuel constraint, then in such a case we can combine these generators into one generator, one composite generator, which is this GS. And then resulting problem will be only this, only two generator problem. So we can reduce, in this way we can reduce the dimension of the optimization problem. The sum of these cost curve is the overall cost curve, and PS will be sum of these generator. But how to get that cost curve? What we can do is we can linearize each of these F1. First of all, we can, what we have already seen that how to piecewise linearize the cost curve. We can piecewise linearize all these cost curve. That you can do. And then just as we did here, we reordering, arranging in ascending order. This is one of the way. This can be done easily. Using quadratic also we can do. Then we have to follow a iterative algorithm. And between, we can increment lambda between lambda min and lambda max. And for each of the lambda, calculate this P1, P2, P3. Because we know that df1 by dp1 or dfi by dpi is equals to lambda. We have this equation and we have this equation. You can solve them and get the value. Okay. Moving on to the next part, which is this linear programming. Now we have piecewise linearized this quadratic cost curve. So we had this quadratic cost curve and we have linearized it, piecewise linear. This was the quadratic cost curve and we have made segments. We have piecewise linear cost curve from quadratic cost curve. We want to use it to do economic dispatch. We have already done that manually. This was the manual method of doing that. By hand calculation, we can do like this. But if we want to write a program for optimization solver, in that case, we can formulate it in this way. Now the cost curve will become like this. So this is the minimum cost and point is P minimum plus whatever is adding here. If it is this one, P1, then the slope of this multiplied by this difference. Will give me sum plus Sij slope into Pij. Pi min, Pi min. This is for each generator. For each generator, now the cost curve is like this. Initially, the cost curve was AP square plus BP plus, which was a quadratic curve. Now we have changed it to in this form. So FPI is Fi min, same is written here also, min plus slope into this difference, or wherever it is. Let's say if it is this, then the slope of this segment into this total length, we will reach this point. Right? Let's say the generation come out to be like this P1 dash. Then this segment is utilized fully. So cost will be F Pi min plus slope of this Si1 into this difference P1 minus Pi min. The second one be Si2 into P1 dash minus P1 because we have only this much. Okay. Same thing is written here. We have these three segments and total cost will be minimum plus sum of each of these individual segments. But now Pij is a variable here. Initially, when quality cost curve were there, we had only three variables, P1, P2, and P3, each for each of the generator. But now for each generator, we have three segments, P11, P12, P13. We have three variable for each generator now, P21, P22, P23. Similarly, P312, P33. We had three variable, now we have 9 variables. So all these are variables. Pij are variables. These are variables. And these are variables are between 0. Each of these are non-zero. So this is Pij here, Pi, not Pij. It is P, let's say 1, 1. This is P12, this is P13. P13 is between 0 and this value. P12 is 0 and this value. P13 is between 0 and this value. This width we need to no. We already know that. That's the limit for each of these variable. Same thing is written here. Earlier we were having Pi less PIS between Pi minimum and Pi maximum. Now this is replaced by these three constraints for each generator, for each of the segment. Same thing is written for each generator and for each of the blocks. We have this constraint. And then overall P generator will be, Pi generator will be Pi minimum of that generator plus individual, sum of these individual variables. Pij summation over J. So if we have three time blocks, three segments, then let's say this is for generator 1, I'm writing. This is P1 is equal to P1 min plus P11 plus P12 plus P13. This will be the overall generator output. And sum of Pi is equals to P load. This was already there. The only thing which has increased is this, and this has been modified, and the cost function has been modified. Okay, now we can use it, and we can give it to any solver, and solver will give us the output. This way we can do. This is without network. Now, if you want to include network, then two more equations will increase, two more type of equation, but number will depend upon how many lines are there or how many nodes are there. One will be KCL and another will be KVL. So KCL says that at whatever current entering should leave, right? Entering current should be equal to the output. So here, same thing, we can expand it to power also. At any node, what is the power injection and what is withdrawal? So that we write in the form of this using DC power flow, because we want to do everything in linear programming framework, and DC power flow is linear equation. B into delta, where B is a matrix, theta is a vector. This is P gen vector minus P load vector. For each node, difference between generation and load. Let's say this is the generation, and let's say on this node or this bus, there are two lines connected. And here we have generation as well as load. Then we are doing generation minus load. So total injection, we are saying whatever injection is happening should be equal to this. Either both line may be going out, one may be coming in also. So difference will be equal to this. Overall injection is equals to outgoing or withdrawal. Injection is equals to withdrawal. That we are doing using this equation. B theta is equals to P gen minus P load. Now KVL we want to satisfy. That means for each line, the power flow should be within the limit. The flow is equals flow on each line. This is KVL. Flow on each line is equals to, let's say, between ij, line I and j. This is theta I minus theta j divided by x I j. This is flow. This is in per unit. If you want the actual value, multiply it by 100, considering 100 is the base MVA, if 100 is the base MVA. Okay, this is line flow, and the absolute value of this should be less than the maximum flow, F max. This is another constraint. These two constraints we need to add when network is also there. So the same thing is written here. B delta is Pg minus PL. These are vectors. Theta is vector. B is the matrix. Theta I minus theta j. Absolute value. This is an inequality constraint. We can make it into equality constraint by adding a slack variable. And we can write it like this. Sij is equals to and Sij should lie between 0 and 2 times of Pij max. If Sij is 2 times of Pij max, then this becomes 100 by Xij, theta I minus theta j is equals to minus. This will become minus Pij max. That means reverse power. Because we are using absolute here, because if there are two nodes, right, I and j, power can either go this way, or it can also go from j to I to j, or j to I to j. If it is considered positive, then j to I will be negative. For that, we have included this, and this can be written like this using this slack variable. Okay. The next one is this lambda iteration method. This is another method for doing this economic dispatch. Here you can by name also, you can say here we are iterating and incrementing lambda, incrementing or decrementing depending upon the error, whether it is positive or negative. Let's say if we have three cost curve, right? Three incremental cost curve like this. And let's say load is something somewhere. Load is such that the incremental cost comes out to be this lambda, some lambda naught. then this means that this generator is fully utilized. P1, P2 is also fully utilized almost. Let us make it like this, almost, and P3 is not utilized. Now, so this is total load. This is equals to load only. P1 plus P2, or let's say this is this is P1 dash, P2 dash, and the sum of these two is equals to load. P3 dash is 0 here in this case. You can sum it. Total they are supplying the load. Now let's say this is the load. If I increase the load by some delta amount, then let's say this is the increased amount. The increased load is such that it intersects somewhere here. Then to meet this load, what should I do? I should increase the lambda. Similarly, if the generation, if load reduces, then I need to reduce the generation. Then I need to reduce the lambda. In that way, we can update the lambda based upon the error which we get. Here we can see the error is summation of generation minus the demand. PR. If this error is positive, that means generation is more than load, which means if this is error, so this is positive, lambda 1 is positive, that means the generation is more than the load. That so we need to reduce the generation, and for that incremental cost, here we can see to reduce generator we need to move downwards. That means reduce the lambda, which is same as incremental cost. We are reducing. If we reduce it, lambda 2 comes out to be like this, and error becomes negative. That means we need to increase the lambda. We are increasing lambda, reaching it lambda 3. Now error is positive. Again, we have to reduce the lambda. But now we know that it will be somewhere in between lambda 2 and lambda 3. So we can interpolate using this. So lambda 3 we can write as lambda, because it will be between lambda 2 and lambda 1. So we can easily interpolate it like this. Lambda 3 is lambda 2 minus epsilon 2 into this slope. Using this, we can easily update it. Here lambda 1 is positive and lambda 2 is negative. Lambda 1 is more and lambda 2 is less. Therefore, above this lambda 2 minus lambda 1 is negative, and this one error 1 is positive and error 2 is negative. So this is negative. Overall, this becomes positive. If this becomes positive, that means lambda 3 should be less than lambda 2, because overall this becomes positive and we are subtracting something. That means lambda 3 is did I make mistake? I think I have made. This was negative. Lambda 2 was less. Lambda 1 was more. Lambda 2 was less. Lambda 1 was more. This become negative. And error was E2 was negative and E1 was positive. This becomes negative, this is positive. I forgot this side. E2 is negative. This is negative, this is positive. So negative into positive becomes negative. Then one more negative is here. So this becomes negative. Overall, this becomes positive. Yeah, so this is positive and negative into E2 is negative. So this becomes positive. So lambda 3 is lambda 2 plus some quantity. Lambda 3 is more than lambda 2. That's we can see here. Lambda 3 is more than. Now it will update in such a way that lambda 4 will be in between, hence it will be less than lambda 3. We can use this interpolation to find out lambda, and we can follow this. And each iteration we can update lambda and again calculate the P1, P2, P3. like this, and again calculate the error load minus summation of pi. You can see we start with some lambda. What we can do, we can take some value of p1, p2, p3 such that it is equals to load and calculate lambda. If we calculate lambda, because we have incremental cost curve for each of these three generator, we can calculate. We know 2a p plus b. We can calculate lambda 1, lambda 2, lambda 3, take an average of these three values, 1 by 3, lambda 1 plus lambda 2 plus lambda 3. This will be our lambda initial guess for lambda, set a lambda. We can set a lambda like this, taking average of these incremental cost. Now starting with this lambda, we can calculate. Now we have the average lambda. For this lambda, we can calculate pi and then check the constraints, whether lower or upper limit are hit, update in that way. If a generator hits it, if a generator goes below its lower limit, then make it minimum value. If it goes above, then make it maximum value and update the rest values and calculate this error. If it is first iteration, then set lambda, okay? If it is no, then check whether error is within tolerance. If no, then project lambda. So project lambda we have already seen. The lambda projection we can do using this interpolation. And then again calculate this. Again, now keep on doing this. And you will find that you can converge. You may not even converge because this has a problem of this oscillator behavior of error, and it is highly sensitive to the what initial guess we take. And also it is applicable only for a given incremental cost. If we have a very complicated cost function, then we will not be able to use this. We need a very basic method. And for that, we go for the gradient method. And gradient, we find out the principle is to find out the minimum by moving in the downward direction, taking steps in the downward direction. This is a function, same minimization of cost, and this is our constraint. We find the Lagrange and then take the gradient. We want to move in the direction of steepest gradient. So next update xn. Here x values are xn is p1 n up to pn n and lambda n. Similarly, n minus 1 will be pn minus 1 previous values. So this is a vector. X is a vector here. Xn and xn minus 1 are vector. This is for previous value. And this vector is for the new values. Okay. And then we subtracted this previous value minus alpha into delta L. This is negative here because we want to minimize. We want to go for descent, not ascent. That's why it is negative here. So these are all incremental cost curve. Okay. The problem in this gradient method is this alpha. The choice of alpha, some choice of alpha may even result in divergence of this method. The solution may not even converge. It is also highly sensitive to the initial guess. That is why we go for this improved gradient method where we eliminate, because we know the power balance equation, we have this power balance equation. In this power balance equation, one generator is always a dependent variable. So we can eliminate the generator, let's say the last one. If we eliminate last generator, then this constraint, the power balance constraint is gone. and it becomes an unconstrained optimization problem. We have n minus generator. Same thing, instead of delta L, now we have delta C. So gradient of C, not gradient of L. Because you can see there is no lambda term here. There are n minus 1 variables here. Earlier we had n plus 1 variables. For n for generators and 1 for lambda. Here we have no lambda variable. We have n minus 1 variables only. We can easily, same update rule we can use here. So this will give us a better result. Still the convergence of gradient method is slow. It will take more number of iteration. We can further improve it by going to the another method, which is the Newton's method. In Newton's method, we have this, sorry. In Newton methods, the principle is we want to make this gradient of a Lagrange function to be exactly 0. And we saw that for gradient and that improved gradient, this choice of alpha matters a lot. And this Newton's method tells us what this alpha should be to make this gradient exactly 0. And this alpha is equals to Hessian. This is called H is a Hessian matrix, or it's a gradient. It's the derivative of the gradient. So we gradient derivative of this gradient itself. So it will become del square L by del P 1 del so del P1 square del square L by del P1 del P2 dou P1 dou P2. Similarly, dou square L by dou P1 dou lambda. So this will be the structure. So similarly, all the terms. It will be a matrix, square matrix. And it's a square matrix. We can take inverse, but in power system, this matrix can be very large. Instead of directly taking inverse is a very computationally heavy operation. So we use Gaussian elimination is the most basic one to avoid this inversion operation. And then other methods are LU decomposition, we can do QR, we can do. Using this, we can avoid this inverse operation, because here this update rule is same. So alpha here is this Hessian. Yeah, alpha is here. I think alpha is, we have made no, this is correct. Sorry, alpha is Hessian inverse, not Hessian. So the inverse. So it will be the inverse of Hessian multiplied by gradient of L minus this will become alpha is Hessian inverse, not Hessian. Sorry for that. And this method has a quadratic convergence. It's very fast convergence. And we can get solution very quick based upon what the tolerance level is. So any questions? One thing is we can do now solve questions. Let us take solve these sample questions, and if we are still left with some time, then I will solve that dynamic programming question. Okay. The first problem is it is similar to what is there in your assignment also, but the dimensions are different. So there are 4 matrices A, B, C, and D. One with dimension 10 cross 5, 5 cross 20, 20 cross 10, and 10 cross 5. And we want to find out how to do this multiplication A, B, C, D such that we require minimum number of scalar multiplications. Now, One can do it in different ways, right? Either multiply AB first, then multiply, we can multiply CD together, AB together, and then multiply these two to get ABCD. Or you can A, multiply B and C first, and then multiply it with D, and then multiply A. Or you can multiply A, B, then here this is like this, AB into C. Or C, multiply C, then multiply D. So there are many ways, but we want to do in such a way that the number of scalar multiplication is minimum. In each of these, the number of multiplication required will be different. They may be same in some cases, but in most of them it will be different. But we want the minimum. How to do that? One simple logic is like this. You can do. There are several ways you can do it, but it is the most simple thing is, yeah, to find out the multiply the matrices. First, multiply those matrices which have largest common dimension, and keep on doing it. Eliminate the largest common dimensions. Keep on eliminating. In that way, you will get the minimum. So here you can see A, B, C, D. In this largest common, if you take this multiplication, the common dimension is this 5. And also, when we are multiplying these two matrices, let's say this is Mn and say PQR is more famous, right? PQ and this B is QR. Then the resulting matrix will be PR. And the number of scalar multiplication required will be PQR. Right? It will be PQR. Here you can see the common is P. You can even write it P into R multiplied by Q. So this is the dimension of the matrix. Not dimension, total number of elements in the resulting matrix. And because here this is Q, we need to have Q such multiplication for each of the element. That is why it is like this PR into Q. You can see the difference here. In this case, the common dimension is 5. Here the common dimension is 20. Let me use some other color. Here the common dimension is 20. And here the common dimension is 10. So largest common dimension appears here, right? 20. So eliminate this first. If we multiply these two matrices, this will require the maximum number of multiplications. If we use this multiplication first, then the resulting matrix is of size 5 cross 10. And the total number of scalar multiplication required are this 5 into 10 into 20. So 1000. Now check, we have now three matrices, A, this one, and D. We have these three matrices now. Now check the common dimension where you get largest common dimension. If we see this 10, 10 is the largest common dimension. The resulting matrix is 5 cross 5. And the number of scalar multiplication is 5 into 5 into 10, right? So it is 250. Here now we are left with only these two. So resulting matrix is 10 cross 5 and multiplication 10 into 5 into 5. Or 5 into 10 into 5. The total number of scalar multiplication becomes 1500. Okay, in this way, you will get the minimum. And you can do it for any of these, any number of matrix, the product of any number of matrix. Find out the minimum number of scalar multiplication. Okay, 1500. Now, second question is this: while solving the economic dispatch problem using LP, increasing the number of segments in the approximated cost function brings the solution closer to exact solution. We have already seen that this is the quality curve and we tried to linearize it, right? There can be several ways. number of steps. Depending upon number of steps, the linearization will be different. And depending upon the steps only, where the solution lies. Suppose the solution lies here, then both are very close. But if the solution lies here, then these two solutions will not be close enough. And this is for two segments. Let's say if there are 3 segments or 4 segments, for 2 segments, if the solution is this, then the error is 0. And if you make 3 segments in this itself, 3 segments, then in that case, if the solution was this, then error would not have been 0. So although the number of steps have increased from 2 to 3, error, the solution is not close to the exact solution. Right? It's not a generic statement, especially for the lesser number of segments. This does not hold true. But yes, if we say 5, 10, and 50, then we can actually say that for a very large number of segments, the solution will be quite closer to the exact solution in comparison to the smaller ones, less number of segments. That can be said. It's not a generic statement and it depends on the segmentation. We need to verify that. That's why this statement is not always true. It's false. Then we have next question. The optimum economic dispatch is the best solution environmentally. This optimum economic dispatch, will it be optimal or best for environment too? And not necessarily, because in economic dispatch we are only looking for minimizing the cost of generation. And each generator also has, just as we have a cost curve, right? AP square plus BP plus C. They also have an emission curve. It is given by some dP square plus EP plus F. These are different from ABCD. They can even be negative in some case. Yeah, they are negative also. For each generator, if you want to get a best solution for environment also, then we need to minimize this emission cost also. And if you want to minimize both, then it becomes a bi-objective problem. We want to minimize cost of generation as well as the cost of emission. It becomes a bi-objective. We have two objective functions here. Okay. So this is also false. It is not a best solution environmentally. The next question is penalty factor in power system economic dispatch is a measure of, we have already seen that penalty factor, which is rho Fi is equals to 1 minus 1 upon 1 minus P loss upon dou P I. It's a measure of the line loss. Penalty factor is a measure of line loss, not generation cost. There is no cost term here. No fuel cost is here. No power delivery. It is only related to the line loss. Then and now it's a numerical question. In a two-plant system, the entire load is located at plant 2, which is connected to plant 1 through transmission lines. So it is something like this. This is plant 1, then transmission line. This is plant 2, and load is connected here. Entire load is connected here. And it is if the plant 1 supplies 100 megawatt of power. So we will change it. With the transmission loss, P loss is given as 5 megawatt. Calculate the penalty. We want to calculate the penalty factor. We know the formula for penalty factor. It is 1 upon 1 minus dou P loss upon dou P1. For this, we need this dou P loss. We need to calculate this dou P loss by dou P1. And for this, we need to know this P loss. And we have formula for P loss for two generator problem. It is P1 square B11 plus 2 P1 P2 B12 plus P2 square B22. Now here only P1 is supplying, right? P2 is not connected to, hence there is no transmission line between P2 and load. And this 100 megawatts, the loss is only due to P1. So these terms will be 0. Here the loss is only because of P1, not due to P2 it is 0. So we have loss function is like this. And this becomes equals to 2P1 B11. This is the loss function. And this is the incremental loss. Now we want to calculate this, but we don't know B11. We know P1 is 100, but we don't know B11. We can calculate it because we know the loss function P1 square B11. And loss is 5 megawatt for 100 megawatt power. We know, so we calculate B11 as 5 into 10 to the power minus 4 megawatt inverse. We can substitute both the values here. We will get incremental loss as 2 into P1 is 100. This is 5 into 10 to the power minus 4. So this becomes 10 to the power minus 1. 0.1. We can calculate penalty factor as 1 upon 1 minus 0.1, which is 1.11. Answer B is correct here. The same thing is written here also. So I will upload these slides. You can go through it. I have summarized this entire week in a very short, very less number of slides. So when you are going to, if you are going to give exam or take exam for this course, these slides will surely help you. You can have a quick glance for each week. That's why I have made these crisp slides, very precise, very short slides, summary slides, and so that you can take benefit. Next is the ratio of maximum demand on generating station to its installed capacity. Pmax by, not Pmax. Pmax is the installed capacity. And maximum, let's say P demand, maximum demand. So this become the ratio of this is what can it? The capacity factor is the availability factor. It is also called availability factor, especially for the conventional generator. And it has to do with the forced outage rate. Forced outage rate. Unforeseen outages. How much, means with what probability the generator is available for a year, let's say 90%, 95%. That is the capacity factor. For renewables, it's very less. We can say in 1 year, the power generated, sum of power generated divided by the installed capacity into number of hours. say number of days if this is power for each average power for each day, then you can write like this. For each hour, if you have power, then you can multiply by 24 also. And this will give you capacity factor. This is considering this force outage rate also. For renewable, this will be very less because summation of P, we know for solar, it is like this. Output is something like this. Night time, there is no power. Morning also, no power. So for this duration, this P will be 0 for these hours. The summation of P will for a PV plant is less than summation of P for a, let's say, coal plant. The capacity factor for solar is around to 20% only. For wind, it can go up to 30-40% depending upon the quality of wind resource. In India, it is less. It's not that high. It's around 30% at some few places. But solar is even less, 20% or even less. Okay, so this is called utilization factor. And one more thing is there, which is load factor, plant load factor. This is average, P average divided by installed capacity, P max. This is called the load factor. This is very simple. We already know this penalty factor is 1/1 minus incremental loss. This is straightforward. And this becomes 1/1 minus 0.2. Okay, 1.25. So last to these three, 8, 9, and 10. What we have discussed, I have done it, since I have presented here in the form of a numerical. We can do it. We can solve it very quickly. Let us do it. Here, what we can do is that this is the question. This is the cost curve, quadratic cost curve. The same thing which I had shown here in the form of steps, that first of all, here we are only looking for the linearization, piecewise linearization. We have to follow these two steps. We already have the quadratic cost curve. We want the linear cost curve only. We can directly do that. So how to do that? We need to calculate the slope. We saw that how to calculate the slope. I'm just showing it for as an example here. So this output of this generator is restricted between 50 and 200, and these are the breakpoints. 4 breakpoints plus these two. So total 6 breakpoints. That means there will be 5 segments. So you can see 6 breakpoints, 2 same as technical minimum and 4 extra. So there are 5 segments overall. There are 5 segments, S1 to S5, and for each of them we need to calculate the slope. If we calculate the slope, so S1 will be this cost of this point minus cost of this point divided by this slope, this difference 20, and this will be slope S1. Similarly, all the slopes can be calculated. Then overall cost function, this F is AP square plus BP plus C. And this we can write it in this linear fashion. Minimum cost plus this slope 1 into P1 plus slope 2 into P2 plus slope 3 into P3 plus slope 4 into P4 plus slope 5 into P5. And P will be P minimum plus P1 plus P2 plus P3 plus P4 plus P5. And P1 lies between 0 to length of each of these segments. This is 20, 30, 40, 40, and 20, which is same here. This is very easy. Next one, last two questions. These are on this economic dispatch. Question is, a coal-fired thermal generating plant has 3 generating units having input-output characteristics and generating limit as mentioned. These are the 3 generators. Their limits are also mentioned. And we need to calculate the incremental generation cost of the plant for a total demand of 400 megawatt. We need to calculate the total. We need to calculate F total, which is F1 plus F2 plus F3. And also we need to calculate the lambda. We have already seen that formula for lambda is P load plus summation of Bi upon 2Ai divided by summation of 1 by 2Ai. We know all the values. So this is A1, this is B1, this is C1, A2, B2, C2, A3, B3, C3. Just substitute these values. Load is 400. Summation of B1 is 5 divided by 2A1, so 0.070 plus 10 divided by 0.04692 plus 3 divided by 0.128. And this is summation of 1 by 2ai. This is 5. This is 1 by 0.07 plus 1 by 0.092 plus 1 by 0.128. You will get some lambda here. Once you get lambda, you can calculate power Pi is equals to lambda I minus Bi divided by 2ai, because we know that lambda is equals to, because incremental cost curve for each generator is equals to lambda, and which is equals to 2ai Pi plus Bi. So from here we can calculate Pi as lambda minus 2ai, lambda minus Bi by 2ai. Okay. Once we calculate this, we need to check what P1, P2, P3 we are getting. Are they within their limits? So we can see here, if we calculate P1, P2, P3, they come out to be within their limit. P1 comes out to be 190.11, P2 comes out to be 90.3, and P3 also is within limit. And we can substitute this value in these cost curves, and then we can calculate the overall cost of generation, total cost of generation. This is incremental cost of generation, and this is total cost of generation. One thing I want to tell you that what does this incremental cost of generation means? If you increase the demand, right now demand is 400 megawatt. If you make it 401 megawatt, then the change in the total generation cost would be equal to this incremental generation cost. You can easily tell for 401 megawatt, the cost will be this plus 18.307. Just a minute. I'll just connect my charger. Fill up. Okay. So this is done. Next question is same. These limits have been changed, but demand is same. This limit of P1 and P2 have been changed. You can see earlier it was 100 and 300, now 50, 150, 50 to 50, now 100 and 200. Now things will change. You can use same formula for lambda and Pi and calculate lambda is same. Nothing has changed, but these things will change because we have changed the limit now. P1, P2, P3 are same, but because limit have changed, now we see that this P1 is more than its maximum limit and P2 is less than its minimum limit. So the first thing we can do is we can set P1 as at its maximum limit and P2 as at its minimum level. And P3 we can easily find out because We have already set the two values. The remaining will be supplied by P3, which is 150. Now, because this is supplying the load and other two are at their limit, this will decide the lambda, incremental cost. We can calculate incremental cost using this. Lambda will be this. This is lambda will be this 3 plus 0.128 P3, 22.2. Now we have to check the condition. For the generator which has hit the maximum limit, its incremental cost should be less than this increment, than this lambda. And the generator which has hit minimum limit, its incremental cost should be more than the lambda. We have to verify that. If we calculate lambda 1, so it has hit the maximum limit, its incremental cost should be less than lambda. This is satisfied. Now for third generator, incremental cost is less than lambda. It should have been more than lambda because it is a costlier generator. That's why it is on its minimum limit. It should be more than lambda 3. It is violating the condition. That's why P2, that means the P2 cannot be at its minimum. But we know that from here we can see P1 can be at its minimum. Now what we can do, earlier we had set both of them at their limits. Now we set only P1 at its limit, which is 150, and subtract the demand. The remaining two generator will supply 250 megawatts and solve the economic dispatch for these two generators. Then if we solve, we get lambda is 20.45. P2 is 113.64 and P3 is 136.36. Both are within their limits. And we can calculate the total cost, is which comes out to be 5197.05. Now I think this is the last question. Do you have any doubts, Shiva? Yeah, so I was telling you that. Okay, let us then quickly solve this question. Forward recursion takes little more time, so I will solve it using the backward recursion first. I will quickly just write it here, otherwise because time is up. Here is it. Yeah, I will do it for backward. In backward, what are we doing? We are starting from the last node and we move backward. So here number of stages are stage 1 is this, stage 2 is this, stage 3 is this, and stage 4 is this. We have 4 stages, so n is equals to 4 here. Now we can write 4 is last one, this j, we are starting from here. And if we want to see this, we are moving backward. For this, we have G, H, and I as S. So first I will write it. Fn S and Xn is equals to CS Xn plus F n plus 1 star. So the cost for traversing from moving from S to X, Xn, and this is for cost for the n plus 1 onwards stages. Here we have only so n. Here n is 4. We are calculating for 3. After 3 we have only 4. So this will be 4. We write it for 3 and when it is F3 S. S is For first stage 3S is this set G, H, and I. We have 3 nodes. And Xn is X4. And if I write it here 4, then this is 4. So in this case, there is no other stage, right? There is no fifth state. So this term is here 0 in for letters for this X4 and S is correct GHI. And so we know this, we can write directly here for different S values. We can calculate F4 as X4 and which one is the optimal out of that, which is X4 dash. Right, so S is G, H, and I here. G here is 8 from, if you want to move from G to J, then cost is 8. From H to J it is 7. From I to J it is 9. So extra X4 dash is J. Here only one. This is for n is equals to 4. Similarly, for n is equals to 3, we can write F3 X S 3. S X3 is equals to CS X3 plus F4. Now we know this 4. We have S. In this case, S will be this set of E and F. E and F. Now here we have to write G. How do we move from? How do we reach? What will be, if I'm here, what is the cost from going here to here? That we want to calculate. Right? From E to G, how do I get? How do I go? And this value we have to write here. And here it is F3. What is the minimum value? And which out of E and F is resulting in that minimum value? So we can directly write from E to G, we can go by 8 plus, and G to H is 8. If we go H, E to H is 9 plus 7. You can take this same as. And E to I, E to I, so E to I, E to I is 5. 5 plus 9. Similarly, F2G is 6 plus 8. And this is F2H 7 plus 7, 4 plus 9. Then this is 16, this is also 16, and this is 14. This is 14, 14, and this is 13. Right? So here, what is the minimum? Which one is causing minimum here? This I1, I, this I. If you move from E to J, then moving from E to I and J is economical. So we are tracking like this, right? From J we have reached I. Up to this stage, this path is best. J2, moving from J to I is better. It's economical. Now for n is equals to 2, we have to see F2 SX2 CSX2 plus F of 3 x2. Similarly, now here S will be this B, C, and D. B, C, and D. So I will just write this table quickly. This will be 3. Here it will be E and F only. So this is 3 plus E 14. B to F is 2. 2 plus 13. C 4 plus 14. D is 2. 2 plus 14. And this is C to F is sorry 5 plus 13 and 3 plus 13. This is 17, this is 18, this is 16, this is 15, 18, and 16. Again, we see this is same, 18, 18, same. And this is here 15, 18, and 16. Out of E and F, which one is better here is F is giving minimum. Here both, either of them, here either of them. So now we say, here we are reaching up to, from I to JI. And here we see F. Let us see n is equals to 1. We will find the final one. For n is equals to 1, we have only A, and options are B, C, and D. From A to B, it's 5 plus, and B cost for B is 15. From A to C is 7 plus 18. And from A to D is 6. This is 20. This is 25. This is 22. So this is minimum, right? B. So which is giving us minimum B. The path is A to B, then B to B. Which one is giving minimum? F. Now F, which one is giving minimum? I. And I to J. So this becomes the path, and minimum cost becomes 20. So this is for backward recursion. Similarly, we can also do it for forward recursion. We'll find answer will be same, but backward is little computationally more easier. Requires no number of less computation. So we stop here for today. So this was the entire week one we discussed today, and we also saw the sample questions. We'll meet next time, next Tuesday. Okay. Thank you for joining, Shiva. Do you have any doubt?